Hello, my name is Gonzalo Abad, and in this video tutorial we are going to see how to do the grid converter implementation in a wind turbine based on doubly fed induction generator. All the information related to this topic can be found on these books, the English version, Doubly Fed Induction Machine, Modeling and Control for Wind Energy Generation, and the Chinese version. Both books edited by Wiley. So if we go to that books, we have one chapter 2 related to this topic, back-to-back power electronic converter. And if we go to page 2 of this chapter, this is the scheme, this is the power circuit and control strategy that we are going to implement. We have already made in previous tutorials all this part, and the remaining part is this one. This is what we are going to do in this video tutorial: the grid side voltage source converter implementation and its control. And we will do it in MATLAB Simulink. Okay, so if we open MATLAB, we have already created the Simulink file from previous video tutorials, and this is our starting point. So if we go to the power circuit, this is the thing that we need to implement. Okay, so let's go to the Simulink program. It's here. Let's do it a little bit bigger. And the first thing that we need to do is eliminate the DC voltage source, and we need to duplicate the power electronic converter. Let's rotate it and then flip the block. Yes, it's okay. Then we need a DC bus capacitance here. Therefore, let's open the library. And from the power library, it should be, that element should be, for instance, here. So let's take, doesn't really matter which one we take. Let's rotate. And we take only a capacitance of value C-bus. We can set the initial capacitor voltage to the DC bus voltage, to the normal operation DC bus voltage, or just to 0. Let's do it at 0, for instance. And then we will need to measure this voltage. So let's take this DC voltage from this part, branch voltage of the block, which is already prepared. Then we can eliminate also the name. Okay, we can save, and we can do a little bit smaller this element. So we can place it here. Okay. We have the initialization program. From the previous program, I have I have included some new lines. Those ones in here, more specifically. And here is the DC bus voltage that we are going to implement. Then here we have the grid side filter, which is this element. We are going to use only an inductive filter. And sorry, but we will use 2 times bigger filter. It's a quite big inductance, but if we use a capacitive and inductive filter, a combination of capacitance and inductance, we could do the series inductance a little bit smaller, but this is not the objective. And here we have some other parameters related to the control that we will speak about them later. Okay, here we have this. Therefore, we need, as we have said, some more elements related to the filter. So we can use again this element, copy from here, do it a little bit bigger, and we will use, as said, resistance and inductance filter, RG and LG, if I'm not wrong, sorry. And we won't use any measurement in this case. Let's do it in that way, and let's check, sorry, where it is. Here it is, yes, the two names are those ones. Okay, so we copy them. This is the filter that must be placed between here, here. We need a little bit more space for this third wire, and here. Okay, then we need a measurer that could be taken from this part, and this must go to the filter. This is A, yes. This is B, yes. And this is C. A, B, C, and B. C, B, and A. Okay. Let's call to this, we won't use voltage, and let's call to this current IG current. Okay, so this is the power circuit, and what we need now is, in order to operate here with the grid side converter and rotor side converter with real voltages, we need to place into the rotor side a transformer. So let's find the transformer in the library, which is probably here. Let's do it bigger. Yes, this one. We remove the name and we choose a simple transformer like this with parameters we don't really matter, but anyway, let's do it in this way, and let's open again, let's show again this file. Just remember that this machine, that this double field induction generator that we are using has an stator and rotor turns ratio of 1/3. So in order to be able to simulate this fact, we need to include in series to the power electronic converter, and between the generator, the rotor side of the generator, we need to include this transformer. So let's do a little bit of space. like here. Sorry, I didn't. Sorry, system units, for instance, and this is okay. Okay. So we need to place it here. Let's do a little bit smaller and a little bit bigger. Seems that everything is already connected. So the parameters were F. We can put here PS, which is active power, and this we are required to introduce or to put here volt amperes, apparent power, but it doesn't really matter. Which is important is to place or to do 0 the parameters, since the only thing that we need is the relations between voltages of the primary side and secondary side. So with this we have an ideal transformer. Let's left the values of the magnetizing resistance and magnetizing inductance to very high values. So here the only effect of this transformer is just to implement the stator and rotor voltage relation. So okay, so there we have. Okay, let's continue then, doing a little bit more space. Okay, it's enough. So we need to continue now with the modulator, I guess, because the power circuit is already implemented. So we just copy the modulator, the PWM modulator from here. One thing that we are going to do is to set the initial phase of the triangular to 0, because in that way we eliminate some asymmetries that maybe in this grid side converter will be more remarkable. So let's do it at 0 and just do the same for the other whole electronic converter for the rotor side. Then we need to implement the control. Let's see the power circuit from the book. We have already created the power circuit, and we need now the grid side control, which is going to be very similar to the rotor side control. Therefore, one simple thing that we can do is just copy it from here to here. We need some more space. Somewhere like this. More or less there. This is not connected. Yes, now it's connected. Let's move there. Okay. So what do we need from here? Basically omega, we are not going to need it, therefore this is not useful. Neither theta. Stator voltage is going to be necessary. Okay, so if we go to page 60, if I'm not wrong, of this book, yes, here we have the control block diagram, and this is the grid side converters block diagram for the control strategy. So just check here that we need the grid side voltages, the grid side currents, and then we are going to control the DC bus and the reactive power exchange with the grid. Okay, so let's go back to the program. So we will need IG, which is this current, okay, and it must to be positive going out from the converter to the grid. So it's okay. Then here we have the stator voltage. This shouldn't be now in per unit, should be in units, because later we will see that we are going to use it, this voltage, at the controller strategy itself. So this is, and then what we need is the DC boost voltage. Okay, so let's go inside this part. Let's do it bigger. Okay, so one is DC boost voltage. This is going to be QG. This is going to be, we have said that we don't need the speed, we don't need theta. This current is going to be the grid side current, and finally this is the voltage. Okay, so we don't need this block anymore, we don't need this, we don't need this, we don't need this. Yes, okay. So now this is the block. Let's try to put some order here. Okay, QG could be like this, and DC boost voltage reference. Normally, yes, normally we use constant DC boost voltage. Let me check. Yes, in this case we are going to use a constant value of 1150 volts, which corresponds to the AC voltage of 690 volts at the grid, to this voltage. Okay, so here we can put the push. We don't need the rate limiter. But here at the reactive power reference we could use it. And let's put, for instance, 100 kilobars per second, or 1000 maybe in 2 seconds, and the same in negative, 1 megawatt in 2 seconds. Later we will check if this is a reasonable slope or rate limitation. Okay, so let's continue implementing the control. Okay, so first of all we can check, for instance here we need to estimate the angle theta of the grid voltage. Therefore we need to come to this block. We don't really need this, we don't need this, we don't need this, and neither this. And this is theta of the grid. Sorry. And this is theta. Yeah. It is more recommendable to use a PLL, but as we are going to perform very simple and very initial stage simulation, we are going to calculate or estimate the angle theta of the grid very simply by this element. This is alpha and this is beta. So we are going to use just the transformation from ABC to alpha beta, and then we calculate with a tan2 function directly the angle. So this is the plot now, very simply. Then here we need the grid size currents in alpha beta. Again, we are using the same transformation, but we give different names to the coordinates. This is alpha beta. This is alpha beta, and this is alpha beta. So everything is correct. So now let's call to this IDG global, okay, and IQG. Okay, and the opposite transformations should have the same names. Alpha beta, alpha beta. This transformation is like this, and sorry, here there we go. I think that everything is okay. We can save. So now these are going to be the currents. Yes. So let's continue from here. For instance, the current references are going to be IDG and IQG, since we are working with the grid side converter control. Let's have a look. So here it is what we have already implemented. Okay, so from the DC boost voltage, boost voltage, we need this PI regulator, and here we need a constant. We need to connect it here and connect it there. Here is going to be this label like this. Okay, I have forgotten to put here a new voltage, a new input, the DC boost voltage, which is coming from here, we have said. Okay, so let's do it from here. For instance, let's go now to the library, not this one, but this one. And we need a measurement. Yes, let's use the multimeter, and we will use another front to block that we can take, for example, from here. Let's go back there, and this is going to be the DC boost voltage that we can call in this way. So we need to associate from the only series RLC branch that we have. Okay, we will take the voltage. Okay, and later we will use. Just here. So let's take it, for instance, let's take another input, paste, and this is going to be the third one, fourth and 5. Okay, and this will be DC bus. Let's put it there and let's connect to the PI controller. Then this reactive power reference is going to be directly connected. Sorry. And this is going to be not torque anymore, so QG reference. So this is not necessary, it's obvious, and this is going to be IQ J. So I think that everything is here. Okay, yes, this is what we have. We can save. Let's go to the initialization program again, and let's go to the last lines that we have included. Here we have the constants. Here we have the constants that we need. This is 1. Sorry. And this is the other one for the reactive power. Okay, then we need to set the parameters for the PA regulators. In this case, there we have the DC boost voltage regulator. This is going to be, okay, the proportional gain, and this is going to be the integral gain. The output of this regulator means here active power, and therefore we could put here as limitation here we have the active power, and we have a maximum S equal to 1/3. So let's say that we have PS multiplied by U, by S max. Yes. In positive and in negative, the same. Okay. Initial condition, okay. So the maximum active power that should go through the rotor side converter, will be the maximum rotor power, which is given by this value that we have set here. Okay, let's continue with these PI regulators. Let's go to the current regulators, and here we have tuned the proportional and integral gains according to this very simple criteria, which is the same that we have used for the PA controllers of the rotor side converter. So let's call IDG, okay, same names but with G. And the maximum voltage, the limitation, the saturation should be the same here and here as well. Okay, this is for ID and the same for IQ. Well, the same values are useful, so Q, G, and here Q, G. Okay, and here now what we need again is to put here the new input, which is the DC boost voltage, according to its name. Okay, so I think that everything is there. Yes. What else is missing? Okay, those are the constants. IQG, IT. Yes, the coupling terms. If we go to the coupling terms, we need to add these two values. So, okay. We need to do some modifications here. What we need here is IDG and also IQG. Okay, we don't need this anymore. This was for the machine. Okay, so we need only 4 inputs for these multiplexers. Yes, like this. And here we will, the coupling term, okay, this is U4, which is IQ. This is LG, the grid state converter filter. And here we could put this value. Let's copy this side again because it's going to be very similar here, but in this case in positive. Sorry, and this will be U3. Sorry, LG and positive. Okay. Yes, this will be obviously not rotor voltage, but grid state converter voltage, and the same for the Q component. And that's all, I think. Here we do the cancellation of the coupling terms. Here we have the third harmonic injection, nothing changed, and this is the voltage reference. Okay, there is one thing missing here, which is the grid side voltage compensation, that we can do it, for instance, if we take one block like this from here, and just before this block we are going to add directly the grid side voltage. That we can take from the entrance, from this input in here. We could cancel this grid side voltage or help to the PA controllers just here in DQ, but we can do it simpler in ABC just add the output before the third harmonic injection. Okay, so I think that everything is already connected. Let's have a look to the initialization program. Yes. Okay. So now we need to prepare the monitorization or the scope. So let's copy just directly from here in order to be simple. Like this. And we could use the same structure as we did for the rotor side converter. We could use, for instance, yes, this is going to be grid side control, this name, and this is going to be rotor side control. Okay, so here we could use, let's put it there, and this is the one that we are changing, grid side control, and this is grid side control. Okay, so we could say that this is going to be DC bus, and this is going to be DC bus. What happened? Didn't work. Okay, so this is going to be its name, DC bus, reference and actual value. The DC bus voltage is controlling ID in this case, so this is going to be ID G if we want IDG. Therefore this is going to be IDG, and this is going to be IDG. Sorry. Okay, and this will be DG reference voltage, that we are taking it from here. Sorry, it is there, it is there, should be there. Okay, perfect. Let's go back to this window. Here we are. So this is its name, the G. And here we could put the reactive power. We just can watch the reference that we have called QG ref. So this is QG, in this case only reference. Okay, this will be now IQ. Yes, Q and grid. Okay, perfect. And this is going to be IQG. Okay, perfect. And therefore this is going to be yes, QG. Okay, so the names are wrong. IQG. Okay. and this is going to be I V Q J. Okay, here we could leave the grid voltage, and here we could use IG. Therefore, let's call it in that way. IG, the grid side currents, and here we won't use any variable. We will not use this element. Okay, so let's save this element. Let's check again. So everything should be ready. This is the grid side control, and this is the rotor side control. Okay, let's go again to the initialization program. Let me emphasize that as we are going to do a startup of the machine, of the generator and the wind turbine, very strong, let me say, we are going to start up the grid side converter, the rotor side converter, the wind turbine model, everything all together at the same time. Let me put the inertia as we have at the beginning, a little bit bigger, 127 kilograms multiplied by meter square. So we can run the program. Yes. So all the variables should be there. Okay. There we have all the variables already loaded there. And for instance, let's start at, let's say, for instance, 7.5 meters per second of wind speed. So this is 7.5, just to do a different value. Here we have the maximum power point tracking. Oh yes, there is one thing missing here. As now, yes, here we have the maximum power point tracking algorithm working. As we have introduced real rotor voltages and currents, here now the rotor side control should consider that. So very simply, we need to divide by U, which is the stator rotor turns ratio of this generator, and here should be placed at the rotor currents, and finally, again, let's do a little bit more space if we can. We should do the same at the output voltages. So the control strategy itself works with the generator refer to the stator, but then it creates the output voltages, real output voltages, therefore refer to the rotor, obviously, and the current measurements are real measurements, so obviously refer to the rotor. And the parameters of the generator should be still referred to the stator. So we left them as they were. So 7.5 DC boost voltage, 0, for instance. Here we have initialized to 0, for instance. So let's save. and start the simulation. Seems that is running, so we have been lucky. The simulation is running, and as you have seen here, there is a big overshoot of DC boost voltage. This is because the startup that we are doing is very strong. We are not making a realistic startup because we don't have time to focus on it. And during this startup, the rotor side converter and the grid side converter reaches its stable operation point. So the DC boost voltage is going down. At the maximum active power that we have set, this is the current that it corresponds. So the system is running. Let's wait. And now it seems that the current loops are working. Once we have a quite a stable, well, still oscillating grid side performance, we have also the rotor side converter working properly with current loops working properly and torque loop working properly, and therefore the speed moving by means of the maximum power point tracking control working to its optimum speed, rotational speed value according to the wind speed that we have set. Okay. Still moving the speed. And here we can see the grid side converter performance. Here we have the 1150 volts more or less control. In order to do that, we need something like 190 volts amperes at D current. These are the sinusoidal currents, and these are the voltage references. Very small voltages because, as you remember, we are using a feedback voltage of the grid voltage. Therefore, and what we are watching is just these voltages right here. Okay, so more or less we have reached the steady state, and let's now simulate a different operation point at 11 meters per second of wind speed. In this way, the MPPT algorithm, control algorithm, operates with less torque and higher speed. This means that through the rotor we have more power because of this current, and therefore we see it as a perturbance. We could consider it as a perturbance at the DC boost voltage. So now this current is moving as well. Everything, the operating point is moving, and here we could also just perform a variation of the reactive power at the grid side converter. let's put, for instance, a negative value of 400 voltamperes, reactive voltamperes. This is the variation, and therefore the current, the IQ current for the grid side converter is also being modified. Still the maximum power point tracking algorithm working. Now we have crossed more or less the synchronous speed. So here we have rotor currents which are almost constant, and now we are at hypersynchronous speed. Let's wait for the simulation. Here the rotor the rotor active power goes increasing again because we are in hypersynchronous operation. The current is going up. And here in ABC the current is also going up. And here we have reached the 400, negative 400 reactive voltamperes at the reactive power of the grid side converter. So here we have a stable reactive power and current. We are still moving 200 amps in active power and 470 something in reactive power, which means that we have almost at this point 600 amps. This is the torque and this is the speed. The MPPT is still working. Just remember that we have an indirect speed control. We don't really have a reference for the speed control. The rotational speed of the shaft is indirectly controlled. Let's wait a little bit more. This is the speed. Then now it seems to be reaching to the steady state. For the rotor side voltage, the grid side voltage, sorry, this is the variation from the grid voltage, very small, 57 volts in D and something similar in Q. And now we have more or less stable operation conditions, not really rich, but more or less we have. So let's stop the simulation at second 6.3, for instance. Let's wait. And now we stop the simulation, and this is what we have achieved. So let's focus, for instance, at the grid side converter in the very last part from 5.6 seconds. These are the ABC currents. These are the D and Q currents performances. This is the DC bus voltage, and these are the voltage references before the feedback forward term for the grid state converter. We don't have yet the steady state, but we are very near. So 5.6 more or less should be, sorry, should be somewhere there, more or less, no, somewhere there, yes, more or less. This is the rotational speed, not at the steady state yet, but very near. This is the torque. This is the ID current for the rotor. This is the IQ current. These are the stator currents. These are the rotor currents, and these are the voltage references for the rotor side converter. We could do a bigger zoom. We could see with bigger details the current performances and voltage performances for the grid side converter. And that's all, more or less. So I hope it was interesting and useful for you. Thank you for your attention.